Okay, here we go. Welcome to episode 4 in the series where I am building a CNC machine from scratch. In tonight's live stream, we're going to be looking at locking down some of the variables of the components that we need to order in order to be able to take this project to the next step. A lot of what we've been doing at the moment has been fleshing out the sort of design, very loosely blocking things out. The challenge is now going to be, as I say, to lock down certain components and get them ordered, and hopefully we can then move on to other parts of the overall project. As a recap, this project is to build a CNC from scratch in order for me to be able to build a Fender style jazz bass. And I will quickly do a rundown of the machine that we're building and why we're building it. So this is the Fender jazz bass that we're building. This is a mock-up using some scrap wood and using the CNC machine that I currently have restored to a operational status. I wouldn't say it's fully restored, but it is working. The base body I'm really happy with, but the neck not so much. There's a few defects in the neck itself. You see there at the top in the headstock there's a bit of an issue, and also on the back of the neck in the transition from the neck into the headstock there's some issues, and that is because the machine that I'm using is too small. It's a 60/40 CNC machine, meaning that it has a work area slightly smaller than 600 millimeters by 400 millimeters, and this neck is approaching 900 millimeters from heel to the headstock. So there's quite a bit of material that needs to be machined outside the bounds of the machine. And what this means is it complicates the operations. It means I've got to flip the machine over, I've got to flip the workpiece around before flipping it over and then flipping it round. And all of these flip and rotate maneuvers are inducing errors into the final design or the final result. So I'm building a CNC machine that will cope with the neck. And this is the space that we've got to put it in. This is the workshop downstairs. The CNC, the 60/40, is underneath my face cam. And the machine is going to go in front of this window. So that's where we are placing the machine. But for right now, we need to start, as I say, locking some things down. So without further ado, let's get into this. Let's get the files up and running. And to start, what I've actually done is I need to work out. Let me bring up paint, right? That'll probably be a good idea. All right. I'm going to quickly just annotate what it is I'm trying to do here. So we have a CNC machine which consists of 3 axes, X, Y, and Z. So X is side to side, Y is front to back, Z is up and down. Now, if we were to take the side to side motion, that would be represented by where this machine, the width of this machine on the bench. So what I need to figure out is how long do I need the ball screw to be in order to be able to machine the neck of this guitar. So we're gonna have, let's just draw this out, and this is gonna be horrible because this is paint and I'm trying to do this with a mouse, so this is gonna be like horrific, but hopefully I can get my point across in this little doodle. Right, okay, so let's undo that. We've got a C channel, right, or a beam that we're going to have as the structure of the CNC machine itself, the frame, if you like. And that's going to hold a motor and a ball screw. Now, the ball screw is the piece of the motion system that rotates and converts rotational motion into a linear side-to-side motion. So that will be represented by, let's draw this. Oh. Write that again. I said this would be horrific, didn't I? And I wasn't wrong. Okay, so this is the lead screw. The red box is going to be the lead screw. Now, there's portions of this lead screw which are pivot points, like a stub on either side, and then you've actually got the thread of the ball screw itself. So that doesn't go end to end. That only goes so far up the shaft of the screw. So let's mark that out. So this area here, and let's mark it blue. Can I do a bucket fill in there? Yeah. So let's say that is the area of the ball screw. Mounted on the ball screw, we're going to have our Z-axis. And our Z-axis is going to hold the tool that is going to do all of the machining of the workpiece. So let's represent that with an orange box. I'm going to put that just here. Okay. This orange box represents my tool. Yeah, the machine that's going to do all of the milling. And this black line represents the actual bit that's going to be cutting the wood. So essentially the work area that this machine can cover is going to be the length of the ball screw, but equally you've got to consider the center line of this box here. Right, so this, and it's gonna travel. This is horrible. I should have really used a brush, shouldn't I? There we go. Right, so this is gonna butt up to here, and this side is gonna butt up to here. So if I was to put this orange box right up to the maximum limit, I am limited by the center line of my tool on both sides, subtracted from the ball screw length. That's complicated, right? Hopefully that come across well, but it probably didn't. But regardless, let's see if we can figure this out in Fusion and make this a little bit more understandable. So I've gone ahead and I've modeled the ball screw. I've taken one of the drawings from the manufacturer's sites, and I've marked out all of the variables that not only control the dimensions of the ball screw, but I've also done that for the nut as well. And in doing so, I've now got the ball screw all modeled up as a master. Just load up the ball screw. So there's the ball screw. And we can program in all of the different variables that controls this, and we can then figure out what is the actual motion of the machine. So let's figure that out. Let's do a mock-up. Let's go here. I'm going to create a new file. I'm going to call this mockup. Mockup. And we're likely to go long today. We're likely to go long simply because we've got to get at the end of this stream. I have to know what what ball screws I'm going to buy for the X, Y, and Z axes, so that I can get the order placed, because they're gonna take a little while to come. So, okay, I've written down some measurements from the machine downstairs that will hopefully help me figure this out. So in this mock-up, I'm going to bring in the neck of the guitar that we're going to machine, like so. All right, so that's ultimately what we're making. Okay, so the next thing we want to do is bring in our beam. So let's bring it in from our estimations, and let's bring it in this, and let's rotate it, just orientate it roughly where we want it. Okay. Give or take, that's the beam. And now we're going to bring in the lead screw. Sorry, I keep calling it a lead screw. It's a ball screw. Okay, let's go in and I'm going to copy this. Copy it into the root of our project. Oh, didn't do that, did I? I copied it into the project. Right, let's move that to there. Move it out. There we go. And let's just drag it in here. And then we're going to roughly place it. Again, we'll use some joints to figure out where things are going to be. Like I say, the accuracy of the placement of parts doesn't really matter at this point in time. We just need a sufficient accuracy for us to get the length of the ball screw. This is the length of the ball screw that is important. All right. Now we're going to put in some models in here, components, to help us decide the length of this ball screw. So I think, first and foremost, they come in various standard sizes. So there's the ones in range I'm thinking of are either 1 meter or 1.2 meters. So I'm going to change the dimensions of this ball screw by coming into the master file. I'm going to change the parameters, and oh, there we go. It's already set to 1.2 meters. So this ball screw is already the maximum size I want to use. So if I was to now go into my C-beam, and we're going to extrude this. I think this is currently 500 millimeters. So if I extrude this another, what would it be? 700? I'm going to save as C-beam 1. Here it is. Get rid of this one in here. Bring C-beam 1 in. That's going to be the right length. C-beam 1. Pop. In it comes. And I'm going to just pop it into place. Roughly halfway. In fact, let's make it halfway, shall we? So we're going to use a jointing system in Fusion in order to orientate the center of this beam over the center of the neck. So let's do that. Let's get rid of the fingerboard. And then we'll create a joint. Select center. Choose C-beam 1. Okay. Somehow that doesn't look like the center to me. Something's gone wrong there, but no matter. No matter. We will continue regardless. I don't mind if it's slightly too big. I'd rather the machine be slightly too big to give us a bit of headroom versus too small. So let's go ahead and assemble with a joint. Align it to this hole here. And we'll bring it up into the center. And let's kick it out this way somewhat. All right. We now have, we look at our beam. We've got our beam and our lead ball screw in position. So the thing for me here is that I need to create a representation of the tool. So the tool, let's go here and go right click, new component, and we'll call this tool. Like so. And we're going to create a sketch in the center. And let's hide the other objects in this drawing. Otherwise, it's going to get a little bit confusing what we're doing. And we're going to use a center constrained rectangle. And let's dimension this out. So I know that the width of my tool is 120 millimeters. And let's call it 200 for argument's sake. Okay. Now I'm going to extrude this by 200. Maybe not. 150. That'll do. That'll do. All right. So what we need to do now is bring ball screw back. And I'm going to right click the ball screw. I'm going to pin it. Then I'm going to create a joint. So let's create the joint. In fact, I'm going to create something that represents the tool. So I want something that represents the tool, so I know where the cutting element is going to be. So let's say we've got a 6mm tool. Okay. And then let us extrude that. Okay. It'll probably be bigger than that, but it's okay. This is going to act as a reference point for us, so we can figure out where things are kind of like lining up. So now we're going to create another joint, and we're going to choose the center point of this box, or our tool, and the center point of our ball screw. Now I'm going to just step this out a little bit. I'm going to bring in the beam. I know where I'm at with the beam. Okay. And then I'm going to change some constraints, right? I'm going to change this from a rigid to a slider. And that means that this object will now slide up and down the ball screw on axis. So if I click on, let me see here. I go minimum. -20, -100, 50, okay, 120. What I'm doing here is I'm setting the parameters under which this box can move. And the maximum is going to be like minus 1,200, 1,300. Okay, not that far. 1,250. No. There we go. If I click on OK now, I should be able to click and drag. Oh, look at that. The tool is moving, but not as I'd intended. Okay. So we need to edit that. Motion. Okay, slide this all the way down. So what I'm looking at here is the end of this threaded bar. We're not going to be able to go any further than that. Unless, I tell you what we could do. Depending on how we have this all mounted up. No, we would. Would we crash? I don't know. I think we might crash. There's going to need to be a bracket on the end here that captures the ball screw, and equally one on the other side, and rotates the ball screw. So hey Brandon, you would love to build a quality CNC, but know how. 2, what parts or items are needed, and 3, where do you buy those parts? Well, that's great. If that's something you want to do, follow along, because we are building this real time in these live streams. I'm going through the process of designing it in Fusion 360, and we will move into actually building it and getting it up and running. I'm building this all with freely accessible tools. So like I say, I'm using Fusion 360's personal license. I'm going to be using some 3 electronics tools because I'm going to be building the controller from scratch as well. So, hey, CE Waffles, welcome in. How you doing? I think I need to move my face cam because I get, well, mind you, it could be a good thing that my face gets covered up. We're gonna go long tonight, CE Waffles. We're gonna go long. Oh, look at that! Look at that little icon you got next to your name. Pretty cool, huh? Anyway, so I'm gonna take the edge of the tool to the end of this ball screw, right? Just to, like, and say minimum is 0 from its current position, and then we're going to go plus 1,100, which it can't go that far, right? So let's bring that back 1,000. Okay, 20, 15. There we go. Yeah, fancy. But Brandon, yeah, follow along in this series. We're building this machine real time. So I'm gonna detail and show the process that I'm using to figure this stuff out. Ultimately, a CNC machine consists of 3 components. You've got your motion system or your frame. That's your X, Y, and Z axes. And the machine will move in those 3 axes independently. The second thing you need is a mechanical component. So that's how do you make that motion system move? So that's stepper motors and ball screws. We're dealing with ball screws tonight. And then thirdly, you need a controller, an electronics controller that tells or instructs those stepper motors to move at a given rotation, at a given speed. So right now, we're kind of like getting a ball of clay and squishing it around until such time as we get something which resembles a CNC machine enough for me to be able to go out and buy the components. Right, so now we can see this is constrained along the length of this rail. The motion is constrained to the maximum. Let me get rid of this side panel, just get a bit more screen real estate going on here. So it stops at the end of this ball screw, just here, the actual thread. And then I can drag it all the way over, and it stops at this side of the thread also. So I might be able to push this a little bit further with a bit of clever design in how this is going to couple up with the Z-axis. But that remains to be seen. That remains to be seen. So I'm gonna say that the tool cannot move beyond the bounds of the thread of the ball screw itself. So let's bring the neck of the bass guitar back into play. And the question is do we have sufficient room to machine the neck? So we've got good access here on the left-hand side, and we've got good access here on the right-hand side. So this 1200 millimeter ball screw is definitely where we are at. That's great. So I'm gonna write this down because so we're using, we were originally looking at a 12 millimeter ball screw. We're now looking at a 16 millimeter ball screw. 16 millimeters in this section this section here where the thread of the ball screw is, this is 16 millimeters. The reason I'm going for a 16 millimeter ball screw over the 12 that we've been looking at so far in the streams is because I actually went and looked at my 6040 machine. So this machine's much smaller than the one we're looking to build, and that's got a 16 millimeter ball screw on it. So I don't particularly want to have a machine that is double the longest length that I've currently got running a smaller ball screw. I think what's likely to happen is that it's going to create whip movement in the screw. And I think the thicker screw will mean it will support itself a little better than a smaller one. It's going to cause me some challenges in terms of how I'm going to design this, how I'm going to get this to fit. In the last stream, we were looking at a 2080 aluminium extrusion. And I've actually come back to the 4080 C-beam. And there is good reason for that. So thinking about it, with the distance that the x-axis is covering, this is going to be plunging, I don't know, probably a 1/4 inch bit into hardwood, possibly aluminium in the future. I don't particularly want a long length of extrusion to flex. The longer that beam is, the more likely it is to flex. Now, yes, I could get some smaller pieces of extrusion and bolt them down the edges and construct a C-beam. But that's additional effort, additional engineering that I've got to do, and it still may fail. Whereas if I have an extruded C-beam, it's one homogeneous piece of material. It's one lump. It's been made like that from the beginning. It doesn't have like gaps where there's areas where it's not attached. It's attached along its, throughout its entire construction. And the fact that it's got this C shape means it's going to resist bending. Does that mean it's immune from bending? Absolutely not. But for what I'm looking to do, I think I can get away with it. But only time will tell. Only time will tell. So, let's go and look at AliExpress. So we're going to be buying the components from AliExpress. Let me just jump here and bring up the window I want to show. So it's going to take a while for some of these components to arrive to me. Which, bit of a pain. So this was the ball screw that we were originally looking at. So this is an SFU 1204. Well, we're going to change the SFU, and we're going to change that. Let's pop it in here. And we're going to go to a 1604. We get a bunch of different ball screws turn up. So they're a little bit more expensive because there's more material. There's going to be more of this to be shipped, all of that sort of good stuff. So we're on a tight budget. we're in incredibly tight budget, so we're likely to go down the road of buying the bare minimum and manufacturing or machining, 3D printing if necessary, other components to make this work. So the cheapest one I've got here that I can see, this is just a ball screw on its own. What is this? Let me change. Okay, they don't they don't have what I want in stock. Okay, let's see here. Okay, that's 16.99. Okay, well, let's see what this looks like. First and foremost, look out for... Okay, so we got free shipping on this, which is good. We want to make sure that we get the right length. So if we don't have the length that we want, awesome. That's just amazing. Yeah. Okay, let's go back to this one up the top here, this first one, 23. 1100. They got an 1100 one for £50, £52 free shipping. So can I get away with 52, sorry, an 1100 as opposed to, I think we're using a 1200 in this drawing. So let's modify that. Pop this out. And let's grab this ball screw. And we're going to change it now to 1100. So we can come in here and change the parameters that I use to drive this ball screw. Change it to an 1100 millimeter ball screw. As if by magic, that changes its size. We'll save that. And then let's jump in here and we'll get a warning. Get a warning in Fusion to say, hey, your component is out of date. It's absolutely fine. We right click. Get the updated component. We're all now up to date. Bring our tool back in. Okay. So we need to adjust. No, we'll leave it as it is. Let's bring the neck in. Okay, so we're tight. We're tight on this side of the neck. But we got quite a bit of room this side of the neck. So that'll mean that we're not centered over the neck itself. So less than ideal by comparison to what we had before, but it will work. We know that that will work. Okay, well, let's keep looking, see if we can find a 1200 millimeter ball screw. Okay. Okay, 1605. But no. think we may have to go with the 1100. 12. And this is the thing when you're building something from scratch. You've got to kind of do a bit of rummaging around in the component stores to find the thing that you need. It's it can be a little bit frustrating at times, but this is where you save the money when you're going down a rabbit hole trying to find components. This is where you can make or break a project in terms of the budget. Okay, I think we're gonna settle on an 1100 millimeter ball screw. So we're losing 100 millimeters off the length of the ball screw. Let me just adjust this first joint. Okay, so now we got clearance there. We got clearance there. See if we can just visually represent this a little better. Okay. Okay, so we've got 915 millimeters of travel by the look of it. There we go. So we can see the bit is clearing the end of the neck here. And it's clearing the end of the neck here. So an 1100 millimeter ball screw is going to be absolutely fine for us. So let's get the workbook up and start figuring out how much this job is going to cost us. Because, like I say, we don't have an unlimited budget. I've got a little bill of materials that I'm working on. Let's bring that down into an area you guys can see. Fact. Let's dock it with that, shall we? I think so. Okay. So here's the bill of materials. Let's blow this up a little bit bigger so you guys can see it. Let's get rid of you. Okay. So we've got X-axis ball screw. It's a SFU 1604. The unit cost of that is $52.39. We want one of them. There is no shipping because it's free shipping. And let's grab a part link. Grab that. Insert link. There we go. All right. So now we got to figure out our Y-axis ball screws, and there's going to be two of them. I'm going to be driving because of how wide this machine is. I didn't feel comfortable running a single ball screw down the center of the machine and pushing like just over a meter in one go. So the ball screw arrangement is going to be, there's going to be 2 Y motors that are going to drive this backwards and forwards. So let's go back to Fusion. So we need to figure out, so our bench size, bench top is 700 millimeters. Now we could get 700 millimeter ball screws, but that would mean that we would overhang the bench by quite a margin. And I don't particularly want to do that. So I'm going to grab the, here. Save this mock-up. I'm going to create a mock-up for the y-axis. So let's save a file. Y-axis mock-up. All right. So let's grab master C-beam in here. So this is a 500 millimeter beam. Okay. Let's copy. Rename this as Y. Now, let's have a look at this. What size have we got in here? It's a 525. Let's go 500. That's more of a standard size. Okay, save that, and then we're going to move it. I'm juggling the number of open projects I've got on the personal license. Gary T, welcome in. How you doing? We're going long today because we've got to get some components locked down. Because I'm going to need to, one, figure out how much some of these parts are going to cost me. And secondly, I need to figure out what are the actual dimensions of the parts that we're ordering. So let's move this let's move this component. Oh, I keep trying to rename it. Move. Gary, these are absolutely learnable skills, right? I mean, I've been using this program for some time now. And I built a blaster from the movie Blade Runner, the PKD blaster, Deckard's pistol, effectively. And from that moment on, I realized I was limited by other people's models. And from that moment on, I started designing my own models. It was a massive unlock for me when I decided to, you know, even like just silly little things, like a clip for an IKEA wardrobe, right? It was muscle memory, muscle practice. But this is absolutely doable, right? Okay, so here comes our ball screw, and we're gonna join it to this aluminium extrusion with a joint. I'm gonna stick it there, the reference. And now we're just gonna shuffle this loosely into position. Oh, Fusion's having a moment. See this black screen? This is a key sign that Fusion is having a moment, right? So Fusion's gonna do one or two things. It's gonna have a serious think, and it's gonna recover, or it's gonna crash. And it looks like we've recovered. Okay. So I had a bit of an epiphany earlier. Come on, Fusion. Come on. I'm not even asking you to do anything hard. Okay, so there's the lead screw in the beam. And like I say, this is just a mock-up. Complete mock-up. This is not how it's going to be. Yeah, it can do that. So frequently saving your files. I mean, there is like an autosave when stuff crashes. If there's a chance that you can recover your work, but frequently saving your files is key here. For sure. Right. All right. So I had a bit of an epiphany. In that this lead screw, this ball screw, I keep calling it a lead screw, it's a ball screw. This ball screw is way too big to fit into this slot, right? So what I'm thinking is that I reorganize the way this is actually set up. Let me articulate this a little bit better. On the fly, I sometimes struggle to articulate what's in my head. I'm thinking, right, doing something like this. This might look really, really strange, but I think it could work. So if I place the lead screw underneath the beam, like this, and let's say I bring in, this would be the enclosure for the nut. So let's put a joint on that. The CAD for the C-beam is all over the place, but okay, so there's our C-beam and our bracket. Edit joint, that's going to need to rotate 90 degrees, like that. And then what we're going to do is, if I amend this joint here to just push this over and then down. Okay, cool. I'm hoping this is going to make sense to you guys. Hoping. No guarantees. I could probably close this gap. Not that it's hypercritical at this point, because we're talking about the length of the lead screw. So we're unlocking. This is a puzzle. We're trying to figure out the size of the key component that allows us to move on to the next step. It's a bit like playing Sudoku, where you've got to figure out that one number that helps you unlock all of the other things, right? This is what we're doing. We're unlocking the puzzle that then defines how big the beams will be, how many fasteners do we need, all of that sort of stuff. So let's bring in our motor. So if I bring in a McMaster car motor, okay, NEMA 23 stepper motor, and I'm going to go there, the regular stepper motor. Let me just stretch this out a little bit. The body, I know the body size. I'm not too worried about the shaft size, but the body size. Okay, square body 73. Is that the size of the... That's got to be the size of the body, right? So I think that is the one I want. Drag this over. And we're going to choose a step file. I'm going to download. In it comes. Okay, and then I'm going to hide a bunch of stuff from this because it brings in... The model has, like, wires and stuff. I mean... Like, why? But okay. Thanks, McMaster car, I guess. I'm going to select all of this, and I'm just going to get rid of it because it's in my way right now. Yeah, right. The number of times you click Control S to save. Right, we're not deleting these. We're just going to turn them off. So we can't see them. They're there, but I don't want to look at them. Don't like it. Okay, they're all gone. Happy days. I just want to check the size of this body. So we're going to inspect the face to the back by pressing the I key. That's 40 millimeters. That isn't the size of the motor that I'm going to be using. So, what I guess I can try and do then is if I just come into this stepper motor, will it allow me to extrude here? 50, 60, 70. It's about that sort of size. Okay, probably another 5 millimeters. So 35. There we go. Crude way of doing it, but it'll work because it's only intended to be an analog for a motor. So this gives me more of a representation of, you know, how big the motor is going to be, all of that sort of cool stuff. Right, so let's go back into the root of the assembly. And we're going to put a joint in, and we're going to select the center. And then I'm going to stick it on the center of here. And then I'm going to flip it. In fact, no, I'm not going to flip it. I want to see what it looks like here. So imagine I've got the motor mounted with a coupler to this shaft here. I can now, with a 600 millimeter or 500 millimeter ball screw, I can see how big this assembly would be. Right? And it is 596 millimeters. Just double check that that ball screw is 500 millimeters. Yeah, it is indeed. Okay. So if we went for a 600 millimeter ball screw, what would that look like? All right, so let's go into the ball screw mock-up. Let's edit this. And this is where the time that I spent in the previous streams building out the parameters for components, this is where we have huge amounts of power and control now, because we can come in here and dynamically change the size of components. And see the change on the fly immediately. So what is the limiting factor here? The limiting factor here is my bench top. My bench top is 700 millimeters, and I want the CNC to be contained. I want it to be contained on the bench. So if I now inspect the end of this, I want it to be under 700 millimeters. And it is 696. Okay. So let's have a look at AliExpress. We wanted a 600 millimeter ball screw, and it's £23.49. Oh. $23.49. $23.49. We want 2 of these. There's no shipping. It's the same link as this one. Yikes. Okay, so we're looking at £100 already. Now, to some of you guys, the £100 may not sound a lot, but I mean, I'm hyper constrained on the budget. Like, hyper constrained. But this is a really good step. This is a really good step for us, because we're now realizing how much stuff is going to cost me. We're also getting to a point where we can really start designing things. Because at the moment, we've up until now, we've kind of been playing. So that all we're ordering here is the ball screw and the nut. We don't get this coupler. So I'm probably going to need to buy some of the C-beam as well. Ideally, I want to buy all of the extrusion in one go, because then I've only got one shipping cost to pay. But we'll see about that. Like 900 Canadian. Right? So, we're going to be building this in stages. And the reason we're going to be building it in stages is primarily budget. If I had all of the funds at my disposal, I would probably go out to a vendor and I would buy a machine straight off the table and get going, right? But I don't have that budget. So I'm having to buy things in stages as funds become available. I'd love to have a channel sponsor that would say, hey, you know, use this machine. But I'm not there yet. Working on it, but not there yet. But little steps, little steps. So until such time as that happens, I gotta build my own stuff. I just realized I put the motor in the wrong place. Oh, for the lols. Right, okay, let's update this. Close that. The measurement's still correct. Put them in there. There you go. That's using a direct drive. And I think that's going to be big enough for what we need. I will need to double check them when I build this up. We'll need to check the motion. But I think we're good. I think we're good. Okay. We want some C-clips. We'll need some C-clips. We'll need some bearings. I'm probably going to 3D print this this housing because I can. Now for the y-axis, one of the things I probably will be doing is folding the motor in. So rather than having it in line like this, I'm going to fold the motor around and have a belt drive, possibly. Oh, now I've said it, I'm second guessing myself. Okay. So I've got the ball screw. Now I've got to figure out the z-axis, right? Let's go back to that original. Save that. Go back to the original. Mock-up. Okay, so we got to look at how much travel we want to have on the z-axis. The current z-axis has around about 70 millimeters worth of travel, and I'd like to double that. Yes, 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 with the motor sideways. I can demonstrate that here actually. Let me grab the y-axis mock-up. What I'm going to do is I'm going to grab the stepper motor. I'll mock it up on screen so you can see what I'm talking about. So there's the ball screw, right? Let's insert a McMaster car. Let's put in the part number. Bring the step file in. We know the body's not the right size, so that's fine. Just move it out of the way. Hide a bunch of stuff again. So obviously we're not looking at the brackets that would hold all of this stuff together. Okay, so you need to be mindful of that. Extrude. .35 millimeters. Right, so that's the size of the motor that we're going to be using. All right. So if I create a joint now, J on the keyboard. Get into the root first. J for joint. Select the tip of the motor. Let's stick it on the end here. Okay, now I'm going to flip it. Boink. Like that. And then what I'm going to do is I'm going to bring it up here. Like so. Now, this is going to crash. This is why we do stuff, right? You can see the motor crashes. But I mean, is that how we're going to have it finally done? I don't know, to be honest with you. Let's edit this. Let's move it. Oh. There we go. Trying to get this to mock up. There we go. Okay, so the motor will be like this. Motor sideways. And essentially what I'll have is a pulley that goes on the end of this motor here, and a pulley that goes on the end of the ball screw. And then there'll be a belt between these 2 points. And then I will find some way of tensioning the motor. So there will be maybe a wedge on a bolt. So as you tighten the bolt, the wedge puts pressure on the motor and the motor moves vertically in the Z-axis and tightens it up. And then you tighten up all 4 bolts on the motor, holding it in place. And in theory, you could release the wedge then, but I probably would keep it there just to keep it in a point where it's creating tension, yeah, supporting the motor. Yeah, so this would be mounted like this, folded in on itself. Now I've been going over in my head whether or not this is a good idea, because the belt has the chance that it can stretch. So I kind of been thinking, do I, don't I, do I, don't I? I did think about doing it for the Y-axis, and then I kind of started settling in on having it inline, direct drive. It simplifies things. Yes, I do lose a bit of space on the bench. So I'm still, right, even now, as I'm debating this, I'm still in 2 minds as to whether or not to have this motor like this, or to have the motor direct drive. I just don't, I'm not convinced right now. Direct drive is going to be better. It simplifies things. It means there's all the power from the motor goes to the ball screw. Is no chance of it skipping teeth. So, for example, if the machine is trying to cut through quite a hard piece of material, it could actually, if the tension isn't right on the belt, it could throw a tooth, jump a tooth, where it wouldn't do that with a direct drive. Yes, it can skip a step, but that's always going to be, unless it's a closed loop system, that's always going to be a bit of a challenge. So that's kind of where my head is at in terms of that. But in terms of like Z-axis movement vertically up and down, the current machine has around 70 millimeters worth of travel on a 150 millimeter ball screw. And the reason for that is the same reason that we've got this constraint here going left to right. It's the center of the clamping device holding the spindle. It's the size of that will determine how much travel it has up and down on the Z-axis. So that clamping system is 70 millimeters. So you can see it's roughly half the height of the ball screw, 150, which is about right, because when you think about it, the length of the ball screw not only is the thread of the ball, it's also the stubs either end. So that kind of makes sense. So it's about half. So if I want, let's say, 140 millimeters worth of travel, I'm going to want a 300 millimeter ball screw. So let's have a look at AliExpress and see what a 300mm ball screw is looking like cost-wise. Okay, not too bad. Yes. Whichever is, so the nut width, it's whichever is the greater of the two. What's going to crash first? The nut or the housing that's holding the spindle? And in the Z-axis's case, it is the housing. So I'm looking at £16 for a ball screw, $16.09 for the Z ball screw. Okay, so copy out these part numbers. So these are going to be not applicable. Not applicable because we're going to make them. We got to claw some money back in the budget. So we will get the components in. Once they're in, we'll model a nut housing. We'll 3D print a nut housing. Now, I fully appreciate that a 3D printed nut housing is not going to be as good as an aluminium nut housing. Totally get that. Is it going to be good enough for what we want? Well, that remains to be seen. We'll look to run once the machine is built, we'll run up a test of the neck and see whether or not we can actually, you know, machine this neck without the defects that we're seeing here. Like I say, we'll use pine. It will be softwood. So if it can't stand up to softwood, then there's no way in hell that it's going to stand up to hardwoods, right? So that is an absolute must. So with that said, we're going to try and model those components, 3D print them, use the tools and skills that we've got at our disposal to kind of save some cost in the build. So I guess the next thing I need to figure out is going to be the lengths of the C-beam. So we'll assume at this point let's redo that joint. I'm going to assume that I am going to mount it in line like so. Now, what I'm looking for here is how much. I mean, this beam is well oversized. Will it allow me to cut into it? I don't think it will. Let's try it. Yeah. Capture position. Will it do it? Will it do it? No. Whap whap. Okay. That's irritating. I guess we're getting into the realms. We're getting into the realms of building this, aren't we? Really. Eek. Okay. In which case, let's just do that. Right. That's the mock-up. Did I put a transmission in here? I did. Good. Can I delete this? Or is it used somewhere? If it deletes it, there we go. We weren't using it. Perfect. Okay, I'm going to create an archive. We're going to move... I'm going to move these things into the archive just to get them out of the workspace. So we know roughly what we're doing now, right? These can go read-only. Check these in the archive. Move. See, this is why you build a machine, buy a machine, right? Because buying a machine, you would not be doing this. You would be receiving it, setting it up, and using it. Haha, you know why. I've gone back to the C-beam for the rigidity that it gives us, right? So, right, let's just quickly save this file. And then we close. All right. The one in there that's still active now because I saved it? Yes. Let's just make read only. All right. So that was an 1100. That was a 600. And that was a 300 if I remember rightly. That was a 300. That's big. 300 is big. I'm going to revisit that. I'm going to revisit the Z-axis. I think 300 millimeters. I'm just looking here at my scale, my digital scale, and it's double my digital scale. That's a hell of a lead screw for a Z-axis. Where's the fun in buying it? You're not wrong. You're not wrong. I mean, if nothing else, I am learning a ton of stuff by building a machine from scratch. You know, is it going to work first time out of the gate? Probably not. But that's part of the learning process. Right, let's get into the build section. So in the transmission, we got a master for the ball screw. Let's go read only for that as well, because we don't need them to be. Right, I'm going to copy this to its current location. And this will be rename. We'll call this X ball screw. And we'll do another copy. And this will be Y ball screw. Okay. So let's go into here and we will go save. This will be the X axis assembly. So let's create a sketch on what would be the x-axis of the drawing. I'm going to insert a DXF file. I'm going to use the C-beam. Okay. Click OK. And then we're going to move the component. Yeah, let's not do that. Move to the origin of the center point of the drawing. And then let's just rotate this 90 degrees. Like so. Perfect. Finish the sketch. And you know what I've done? I've gone and broken the rule. I didn't create a component. Like an absolute buffoon. All right. At least I caught it now. Right, create component. And we'll call this C-beam. That was lucky. That was lucky, because had I carried on the way I was going, that would have been a problem. Okay, so now we want to put a sketch on this axis. Insert the DXF. See, my brain gets ahead of me sometimes. Okay, we're going to move, change the center pivot point to the origin. Now let's rotate it 90 degrees. Okay, I'm going to explain something in a second. Okay, let's extrude this. And we're going to change from one-sided to symmetrical in the whole length. And I'm going to say 1 meter. Just an arbitrary 1 meter for now. We'll refine this. In fact, let's put in a parameter for XC length 1000. Okay, now what I can do is if I come back into here, I can change the length to that variable XC length, and now I can change the variable on demand and be able to modify it and make it fit. So we want to bring in our X ball screw. Our X ball screw needs to be the right size. So let's just double check it is the right size. Looking good, but let's check. Change the parameters. It's 1200. So we want to change that to 1100. Ooh, 1100. Okay, everything else is good. Let's save that file. And then it'll make it editable momentarily. And then we're gonna, once it's finished saving, we're gonna change it to a read-only file. Like so. And then we're gonna come back in here and then we're gonna drag the ball screw into the drawing. Bop, just like so. It's gonna appear. So, which side do I want the motor on, left or right? I think I'm going to have the motor on the left-hand side of the machine. So I'm going to create a joint, J on the keyboard. I'm going to choose the tip of my ball screw, like so. And then I'm going to arbitrarily select a component so I can center the ball screw on. Now I can just jog it around. And bearing in mind, these are not final positionings, because we're going to need to mess with like where this stuff's going to sit, simply because, you know, things will need to be finagled into position, right? So if I now go here, you can see there's a bunch of this ball screw sticking out the end, which is what I wanted. Yeah. And the reason I wanted that is so I can finagle the length of the ball screw. Sorry, the length of the C-beam to match the ball screw. See, that's my brain getting ahead of me again. Right, I'm going to inspect. I'm going to measure the distance between here, on the beam, to here on the ball screw. And it's around about 90 millimeters, give or take. So if I come back into my parameters and I change this to 1090, watch what happens to my beam. Get rid of this a second. Oh, you can see it just jumped. And it's now in line with the end of the screw part, the ball part of the screw. So that's good. There'll be a bracket on the end of here, so that's fine. We can play with that. But I can just change these parameters on the fly, which is amazing. So do I? Okay, okay, my brain is going like overtime right now. So let me explain something. So the machine will be on the bench like this, right? We are looking at where the tool, where the Z-axis is going to be mounted, and we'll place things into the machine this way. Why have I got the C-beam orientated this way? Well, there's a good reason for that. You'll notice this extrusion has like this T-slot arrangement. Chips and sawdust can accumulate in these areas. Imagine if I had the ball screw and all of this C-channel exposed to that area. All of the dust and rubbish that would end up getting picked up in this area without a bellows or a brush arrangement to try and prevent debris getting into the ball screw and into the channel. That's ultimately why I'm facing the ball screw away from the actual tool head. So that's the reasoning behind that. So in fact, before I join that there, I think what I'm going to do is I am actually going to bring in that nut housing. In fact, I'm going to bring in the nut. Just drop it into the diagram. Let's go into here. Let's go into the estimation. And make this read only because I don't need to edit it. I'm going to copy it. And now we're going to move the copy. Okay. Now we can use that component in here also. Just move that up there like so. Cool. So I'm going to just assemble these things. Like so. Before I do that, I want to make that a rigid joint, don't I? Okay. Now I can modify, I can join. That to here, like so. We can change this later to be... Right, let's do it now, shall we? What I'm doing is I'm aligning the ball joint, the nut, with the end. Okay, that is the absolute maximum that can go, right? That needs to be rotated. Yeah. Cool. Let's jump this forward. Okay. Look at that. I can now edit this joint. And I can say that motion on this is a slider. Minimum is 0. Maximum is 1000. Maybe. $980. 985. 987. 986. Okay. So theoretically, I should be able to slide this along here now. Ah. There we go. That is a physical, that's a physical limitation now on that as to where it can and can't go. But this is not, I don't think that's going to be the full extent of it. Or it could be actually. I don't know. Okay, so let's look at this and spot if we've got any problems. I think we're pretty good here. So the next thing we're going to do is bring in the motor, McMaster car motor. Oh. NEMA 23. square body. Looking for the body size. Let's see what this one looks like. No. Okay. Hide these components. Perfect. And now let's extrude this by 35 millimeters. Okay, now we can create a joint with it. We're figuring out whether or not we're going to mount this directly. Are we going to mount this directly to the to this axis, or are we going to leave it? Are we going to fold it into position? Right, let's hide the joints because the joints kind of like get in the way with the little reference markers. So in theory, I could actually model a plate that will go on the end here. In fact, should we do that? So let's create right click, create a new component. And we'll put this as being RHS plate, right hand side plate. And the first thing I'm going to do is going to put a construction plane on the end of the C-beam, and we'll put the sketch on the construction plane. So if we change something in the future, we're not going to lose any of the plane geometry and cause errors and all sorts of problems later on down the line. So the first thing I want to do is I want to capture the mounting holes of the motor itself, because we need something to mount that motor to. It need a bolt screws through it, and I'm already starting to see an issue. We're crashing, the motor is crashing the extrusion. So I'm glad we're doing this. And what we're going to do is we're going to capture that. I'm going to capture that. Just capturing a couple of bits of geometry that I'm going to use to now build up this plate. I'm going to connect these bits of geometry, and I'm going to extend other bits of geometry. That's beyond. I'm just going to bring this down here. arbitrary amount. Let's say 200. Okay. Then let's straighten that up. It's gone all a bit wonky donkey. Okay, I'm just making shapes right now. Not really worried about much in the way of whether or not it's right or wrong, because we'll just build off of this. We'll turn that into a construction line. So I'm capturing the section of the motor housing. And I'm going to just do a quick offset by 0.5 millimeters. Okay. And I've now got a plate. If I extrude this by, let's say 3 millimeters. Oh no, say 5 millimeters. Let's say it's 5 millimeters of aluminium. If I bring in the bodies now that I just turned off, we start to see the machine appear. Ah, silly boy. Spot the obvious error. I've captured the motor, but it's not the motor we're trying to capture. It's the end of the machine. Oh, for the lols. Okay, that's fine. Let's fix that. Let's go back into the plate and edit the sketch. Okay, let's turn all of the bodies off that we're not interested in, which is all of them. To get rid of that, going to get rid of the mounting holes. And this time I'm going to project holes of the extrusion because I need a way to attach this to the machine. Like so. I'm going to bring the ball screw in. And I'm going to project that. Perfect. Turn the ball screw off. Reorientate myself. Turn that into a construction. And then we're going to do an offset. 0.5 millimeters. Click on OK. Now we probably need to think about a bearing in here to carry the plate, but that's absolutely fine. Okay, let's have a look at that now. There we go. It's looking better already, right? So we probably want to think about that a little bit better. That looks a bit rough. That looks a bit rough. Oh my dear. Okay, so that's 5 millimeters. We want a bearing in here, and how are we going to achieve that? We could probably do an insert of some kind. Okay, let's start making some notes, because this is getting pretty like serious here now. So this is the x-axis. And we want bearing, housing, right hand side, and left hand side for that matter. Even though it's the motor side, we need some sort of bracket. So let's have a look at that. We're going to need to capture. This and put a bearing on it, and then we'll have a coupler here. So I'll need to inspect how this is done on my other machine, rather than put something arbitrary in here that means absolutely nothing. So I've got two choices here. I can create a plate like, well, I'm going to need to create a plate like this one over here. In fact, I've gone the wrong way, haven't I? I've drawn the machine, I've drawn this forward when it actually needs to go backward. Okay, let's make a note of that. Side plate, reverse. Get messages here a second. One second, guys. Who is messaging me? Okay, sweet. Go mute. Yeah. Muted. Right, okay. So what I've done wrong is I've pushed this assembly forward when it actually should go backwards. So I think we'll fix that now. And then I can strike that out, my corrective action that needs to be taken. So let's get rid of that. It needs to come this way. Get rid of these arbitrary lines that we no longer need. Okay, I go quiet when I think, so feel free to ask questions, guys. I'm going to dimension this. 120. Then I'm going to go going to make these two lines parallel like that. I'm going to line there. I'm going to make it a construction line, all the same. But I'm going to flatten it. That'll pull it into some semblance of a... There we go. Better. Probably reduce this down further. Now I am contemplating what I'm going to make this out of. Do I get some aluminium and make this out of aluminium plate, or do I get some mild steel and get that cut on my buddy's big laser cutter. And I'm thinking possibly getting my buddy's big laser cutter. I think that would be cool. We'll play with that. Figure that out. But yeah, I've got a bunch of mounting holes that I can use into the aluminium. I might possibly add some more. I'm wondering whether or not to use like some brackets. Do you know like the aluminium extrusion right angle brackets? What do I mean? I'm not sure what they're actually called. Let's find. Products, mechanics, jointing brackets. These things. Right? Do I get a couple of these and stick them onto the extrusion and onto the plate? I'm thinking not, actually, looking at this, because the reasonable chance we're going to crash the nut. There's a reasonable chance we will crash the nut. Huh. Okay. All right, let's get a plate on this side and see what that looks like. So again, let's go into the C-beam, right click, new component, and this will be the left-hand side plate. Again, we'll use a construction plane, good positioning of everything. Stick it on there, click OK, and then we're going to stick the sketch on to there. Now I'm going to project this to start with. And then I'm going to project turn off the ball screw nut housing and the beam. Is the beam itself. Okay, cool. Project that line there. Now I'm going to turn the motor off as well. Not before I select the holes, the mounting holes of the motor, because I need to bolt through. Okay, good, good, good. Turn the stepper off. I think we can finish the sketch, right? And we could extrude this 5mm. If I turn everything else back on, jump to the root,
And there you can see we've got an issue, right? With placement of the motor, it's going to crash. Hey. Right, so I need to kick out the lead screw joint. Which I think this one? It is. How much clearance have I got? Now I could probably bring this in a little closer if I thread the hole. I could possibly thread that hole. That might work. Okay, so what is the height clearance here then? If I inspect here to here, is this enough height clearance? 120 millimeters. So if I, yeah, that probably needs to come down a bit more, doesn't it? I would say that probably needs another 80, yeah, another 80 millimeters. So let's go into the right-hand side plate, and we should be able to update this one thing. Okay. And the other one updates as well. Look at that. Ain't that cool? That's well cool. So now I need a series of holes that will represent the mounting point for the Y-axis ball screws. So essentially this section of these vertical plates, they connect to the Y-axis. How can I demonstrate this? Let me do a quick drawing, right? This is gonna look so horrible, right? Because my drawing sucks. So we've got the C-beam, right? Let's draw this from the right-hand perspective. It'll be a little bit easier for me to do that. Art was never my subject, right? So forgive me. That was horrible. That's horrible. How can I demonstrate this to you guys in a way that I can see it in my head. I can see it in my head, but I can't articulate it very well. So I tell you what I'll do. Yeah, I will kind of butcher my assembly, right? I'm going to save this a second, right? I'm going to go into my estimation, and I'm going to bring in the C-beam, right? Imagine this is the machine kind of like all assembled up, right?
So there's going to be a rail. Yeah. There's going to be a rail that will have like a carriage on it, top and bottom, and we'll put a series of holes through here to receive the carriage, bolt into the carriage, and that then bolts onto there. And that's what will allow this to slide up and down the axis, right? That's ultimately what we're going to look to do. Hopefully that makes sense. Now, the interesting thing here, I just want to see how much. I'm just going to mock this up because I'm curious now in my head how much room I've actually got for machining. Okay. Okay, it's going to be something like this, right? In terms of where the machine bed is going to be. I just want to see how much that's going to be. If this is going to be like the maximum. Okay, comments in chat. Or if you're watching on the VOD, comments in the underneath the video. I'm looking at the distance at full extent, right? So let's say I'm machining something all the way down here. We are going to be looking at 180 millimeters. I've got a concern. I've got a concern that we're going to crank this. So the longer the throw on the z-axis, the thicker the material I can put into the machine. But at its extremes, it's going to be the most stress that the machine will be being put under. So what's the thoughts? Do we have any thoughts for that matter? Because that's quite a distance. 180 millimeters. Okay, so what I'm not factoring in here is the size of the Z plate. So the plate, so there'll be an X-axis mount that's going to go on here and on the other side of this nut, right? This nut that we've got that slides backwards and forwards. It's going to wrap around to the front, and it's going to have a series of rails on the front. And that's going to have a plate on it. So this isn't necessarily a true representation of the height. I need to be careful here. Because while something might look awesome in the computer, when you actually build it in real life and you start putting stresses on it, it may not be very happy with me. may not be very happy with me at all. Contemplation. Yeah, I'm just thinking through my actions here. Whether or not this is a smart idea. I'm not sure it is. I'm not sure it is at all. What to do. I think I'm gonna have to sit on this and think about this seriously in terms of how much force is going to be going through here, because there's going to be a plate, as I say, on here. Mock that up. So the plate will be here. Why did you do that? Why did you rotate like that? Come on, throw me a bone. So let's say yeah, I'm starting to question myself now. Seriously question, should I be doing this? Right, so there's the plate that I'm talking about that's going to mount the spindle on. Right? And then if I bring this joint into position, okay, so that's kind of like what's happening here. That's going to slide backwards and forwards, and then that's going to have my spindle hanging off of it. And this is where the Z-axis ball screw is going to be. And I got to figure out whether or not there's going to be too much force going through there. It's going to be a rail on there, top and bottom, so that's gonna hold it. That's gonna be fine, right? Isn't it?
Lots to figure out, huh? I think I want to unbias this. Okay, let's see if I can figure this out. Why has it jumped over? I don't know. Huh? What? Wait, what are you doing? What on earth are you doing? This is misbehaving somewhat. Okay, construction line. In the center of the drawing, please. What? 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 What is this magic? Fusion, what the heck are you doing? Okay. Let's finish the sketch. I gotta delete this. I gotta delete this. Right. Ah! What on earth is going on? Construction plane on. Okay, create the sketch on that plane. Thank you very much. Stop rotating like an absolute doofus. I'm going to put a construction line in the center of my drawing. Right, let's just turn off all of this lot, right? There we go. Center line there. Perfect. Okay. Can turn that back on now, just so I can see what's going on. And if I... $200 by 120. 120? Yeah, I think it's 120. On keyboard camera. No! How long have I been like that? One absolute doofus. Thanks, buddy. Appreciate you. Been chatting away. Okay, it's going to be something like that. But the problem is, then that cuts down on the amount of height that I've got. That's just like going to crash. Yeah, I've got a lot of development thoughts I've got to get sorted out here. Try and figure out these problems. I got 70 millimeters of movement, which is what I've got already, all right? And I want to increase that. So I need to bias that a little bit. So if I was to move this plate, oh, right? If I bias it like that, how long was I on that keyboard camera for? Yeah. Too long by the look of it. Okay, so I've now got 90 millimeters worth of travel. Probably ages. Okay. So that's ultimately what I'm trying to do here, right? Is I've got this beam, the C-beam with a set of rails. And I'm worried that it's going to crank over. G4 years to be exact. Ah, dear me. Dear, dear, dear. Oh. Bring the guitar neck in here. Okay, so there's definitely plenty of room. There's definitely plenty of room to machine this neck. That I'm not overly concerned about. What I am concerned about is how much room I've got with the machine. I'm gonna have to go away and take some measurements and just figure this out, I suppose. It's gonna be a little bit challenging, right? This mock-up. I mean, we've got the measurements for the ball screws, so that we can get those ordered. I'll get those ordered hopefully later tonight. But what I haven't got is my Z ball screw. I want my Z ball screw sorted. I've got to figure out in fact, let's do that. Let's get the Z ball screw sorted out in this diagram. So if I go into build transmission, we go, let's copy the ball screw master. And this will be renamed Z. Okay. And I think on the current machine, it is 150 millimeters. Oh, I got a warning. Danger, Will Robinson. Danger. There we go. That looks better. How much travel has this got? Got 80 millimeters of travel. Okay, what size ball screws can we have? What's the smallest they do? 250? 200. 200 is the smallest. Okay. So the travel on this now is 130 millimeters. Okay. If I was to bring, let's save this, right? Let's bring this in. We could start to, start to figure. Just double check those measurements because I did hit the revert button. Did I revert or did I do nothing? Okay, that's fine. Perfecto. Okay. Let's bring that into our design. Hide. I have to have some means of holding this. Oh, look at that. It's almost like I knew I was going to do that. You definitely see why you pay the money you do for a machine like this. Definitely. Okay. I make this a rigid group now. And I move this, that's all. Right, okay, cool. That moves. Okay. And then if I just quickly model up a new component, call this spindle. Just a representation of the spindle. I don't think it's this big, but it doesn't really. You say this is a low poly sort of representation of the spindle. Okay. So if I now create a joint between that, okay, let's make this lower extremity. Slider. Okay, let's turn everything back on. Should, in theory, be able to drag this around. Look at that. That's pretty cool, right? That's 70 mils. That's 70 millimeters worth of travel. Bring the neck in here. It doesn't look too bad on the surface. Okay, so plenty of room there, plenty of room there. I do want more travel than that. So if I edit this joint, how much travel do I think I've got? So on the nut, it was 130, wasn't it? So I probably, if I say 80, that's probably about as much as I'm going to be able to get. It's all going to be down to the size of the nut. So if I throw one of these in here, right? I'm really messing up my design here, to be brutally honest with you guys, right? But I'm doing it to learn something about my design and whether or not what I'm thinking is viable. Let's bring that in there. That. Rotate like that. Okay. Let me make these two a rigid group. Like so. And now if I joint that, that, okay, I know stuff is crashing, but it's not major, right? I just gotta figure this. Okay, so that's at its highest. Now, if I make this, modify, assemble, rigid group, capture the position this time, yes. Okay. Ooh, what's happened here? Wider. Okay. Not joined. Why are they not joined? Now they're joined. Excellent. Okay, so there's actually a little bit more play in that than there's more in there than... How much more do you think we got in there? Another 10 millimeters? 110? So if I go in here and adjust this joint, and I make this... Oh, cancel. See this, I've lost myself a little bit in my design. I want to figure out spindles joint. That can't be it, surely, your goodness. No, it's not. There you go. -70. That's a bit much now. Okay. Yeah, a bit much. Somehow I've managed to capture this rail. What the hell happened there? I don't quite know what's happened there. I broke it. Right, okay. Okay, let's go 15mm. Okay, edit. 10mm. Hilarious. There we go. So let's get rid of this a minute. Did I capture it in this rigid group? No, this rigid group. Edit rigid group. Yeah, not quite sure how I managed to do that, but we'll just hide that. Just pretend that's not there. It's not there. It's gone. It's gone. 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 Okay. Okay, so we got... How much travel is that? We got 80... Is it 80 mil travel? Minus 70 to plus 10. That's 80mm worth of travel. That's 10mm more than what I've got now. Oh. Ducks. So I think I'm gonna have to live with that. Much as I may or may not like it, I'm gonna have to live with that on the basis that this machine is gonna have very specific task. Okay, I think this is workable. I mean, certainly from the neck perspective. Bring this beam back in, shall we? There we go. Move a component. Okay, so we've got good clearance. Yeah, may need to like drop the head down if the bits don't reach, but we can definitely play with that. And the bit is higher than the plate that we've got there. Okay, so what happens when we bring in the guitar body, I wonder? That I do wonder what will happen. So let's go and grab a copy of the guitar body and bring that in and just see. Let's just see what that looks like. Let's grab this. It was successful, but where is it? Where'd it go? Oh, I can't. Cancel. Go here? Yeah. Right. Move. Oh, it won't let me move it out of here. Why not? Yeah, it won't let me put it into there. I need to put it into a new project. This is interesting. This is why is this not allowing me to move? We need to save it as maybe. There we go. Derived references can only be created within the same hub, within the same project. Please select the design that meets the criteria. What? Huh. Documents in use and cannot be deleted. Probably because I got it open. Delete. Okay. Now what are we using here? Oh, it is the right design, but for some reason it won't allow me to get it. So I tell you what we're going to do. Don't save. Don't know if I did this. I don't think I did this before, but open this. Okay, now we're going to export. Export it as a step file. And then we're going to okay, cool. Okay, I did this before, didn't I? All right, so let's go into the CNC. Let's go upload, select file. This is now the body coming up. Okay, we've got room. We can machine this. No bother at all. Now I want to see if I can rotate this. Can I machine it this way though? I don't think I can. I think I'm asking a little bit too much in that regard. No. I can't machine a body if it's rotated this way, but I can if it is this way, which is absolutely fine by me. As long as it'll fit on the bed, I've got no issues whatsoever. Yep. That's gonna work. Okay, let me just try something here. Let's pin that. I'm gonna create a joint. Bring this that just as a reference. Like so. Make it a motion. Awesome. Go. Okay. Let's create a rigid group. A rigid group. Yeah, that doesn't work. Yeah, more info. What's wrong with it? Compute failed. Close. Okay. I'm going to need to see what motion I've got on the x-axis. Oh man. It's new. I knew this wouldn't be easy, but you know, didn't think it would be this hard. Okay. Okay. Try computing a joint again. No. Okay. Will it move? No. It gives me an error. Okay. I'm gonna have to figure out that joint system. I'm gonna need to figure out that joint system, see whether or not I've got enough travel. That's pinned. That works out, right? But I've got to do the travel backwards and forwards. Represent that ball screw. And this is where, because you allow yourself to just let the timeline kind of rumble on, it starts to catch up with you, and that's what's happened here. It's caught up with us. Huh. Yeah, let's try creating that rigid group again. Okay, now let's see if I can put that joint on here. Once you selected are rigidly joined, part of a chain of rigid joints or pinned in place already, cannot move. Okay, might be the pin that I put in here. Let me unpin the C-beam. Maybe that is what is my boggle. I thought I had to pin it, but maybe I don't. Maybe I don't. Okay, joint. Okay, okay. Bring that down. Okay. Motion. Maximum 590, I think it was. 490. It's a bed slinger. Oh my goodness. Oh, that's hilarious. Okay. We'll work with this. We'll work with this, right? So if I assemble a rigid joint, yeah, capture the position. I want this component, that component. Click OK. And then that moves as well. Awesome. Okay, this has got kind of messy pretty quick, right? Edit the joint motion. Minimum is 0. Okay, right. So that's now got some constraints on it. So at its maximum, can it machine? Have I broken all of my joint system now? I think I might have. Uh-oh. Yeah, my whole joint system is now broken. Okay, let's see if we can figure this out. Let's go underneath. You can probably see better. So there's the center of that. Yeah. Yeah, that'll work. That will work, albeit a bit messed up. Yeah, right? Wait there 1 second. That's not what I wanted. So what's happened is that all my joint system has become somewhat conflated. It doesn't know what. It doesn't know quite what is what. I suppose that's the reason for that is because I started this design as the X-axis assembly, and we've kind of had a bit of scope creep. We've crept in and allowed our timeline to flourish. and this is the result. So yeah, it's it's not quite what we had hoped, right? So yeah, less than ideal. Okay. I think for the purposes of my x-axis, what did we select for my x-axis? Let's check the list. So we chose 600. What are our options? Okay, 600 or 700. 700 is the size of the bench. So that means I'm gonna have motors hanging over. Now, I suppose what I could do is decrease the size of this plate. I mean, what is the size of this plate? $106. I don't particularly want to reduce the size of the plate, because the thinner the plate, the more force, more twisting force that's going to put. The wider that base is, and the more it's supported at the extremes, the more stable and more force that can actually take. So the fact that it's 100 millimeters is probably fine. Yeah, 100 millimeters is probably okay. And there's going to be two rails, one top, one bottom. And there's probably going to be two carriages top, two carriages bottom. So I think in that regard, that's going to be okay. But it's going to be... going to be a little bit tricky, to say the least. Okay. So the question is, so currently we've got a 600 millimeter ball screw that we're gonna mount the motor on direct drive. If I add an extra 100 millimeters, that means the motor's gonna hang over my bench. What's the difference in price? 23, 32. About a tenner. 10 quid. 20 quid across two. What I'm concerned about here is something that I haven't necessarily taken into consideration, and that is this arrangement here, this clamping arrangement. We haven't even looked at that and how that's going to work. And that concerns me a little bit. Just a little bit. How am I going to make that work? How indeed. How indeed. But I think we're in reasonable shape. I could probably put more of an angle on that, right? more of an angle on that. I am so sorry for you guys. You're seeing my inner workings like laid bare. My inner thought processing. So okay, that's okay. So you now see that the machine, it comes to the end of the bed. It doesn't overrun, so that's good. Has it given it much? Has it given us that much though? I think the travel is the travel, right? I'm a little bit concerned about this as well. Yeah. That overhangs quite a bit at the back. I am space constrained. That could work. That could work. A 600 millimeters. Okay. I think the decision is I'm not gonna order the ball screws tonight. I'm going to do some offline thinking, figure out what I'm going to do with these ball screws, and then go from there, really. That rigid group that broke it. So whatever. Oh man, I'm definitely gonna have to take this offline and figure out what I'm gonna do with this. It's the travel on the y-axis that I'm concerned about. So I don't want this to back up that far that it hits the window. That's one thing it can't do. And I think in its current configuration, the machine will do that. I'll just reinstate some of this stuff. So this is on the premise that the machine is... This is on the premise that the machine is on right up against the back wall. And that will crash. That will crash. So I need to figure out how I can... Okay, I need to go away and have a look at my machine and figure out how the current machine is configured. And then I can figure that out from here then in terms of the motion. A little bit. It sounds like I need a bigger shed. Need a bigger boat. Yeah, right. Tell me about it. Tell me about it. But I mean, these are the things that, okay, so the cool thing, the positive to take from this is that I'm finding these things out before I've spent any money on the components, before I've spent money and time building the unit to put it into place only to find and watch it fail. So while you see me just pause and not speak, I'm thinking live that what is actually gonna, how this is actually gonna play out. I'm running computations in my head and scenarios in my head as to, you know, what's gonna happen when I run this machine. And I'm just currently thinking, do I rotate the machine 90 degrees? I've been concentrating. I've been concentrating on the machine, sitting on the bench. We're standing in front of the bench, looking at the machine as it stands. And I've had this in my head the whole time. But what if I rotate it this way? So we are looking at the x-axis. This then becomes this becomes the y-axis. That's an interesting proposition. It makes it, I mean, I wanted it this way because it makes it easier to load materials in, etc. But if I rotate it the other way, I've got a little bit more leeway in the sense of these rails overhanging the machine. When we're in this configuration, right, and it's right the way back, overhanging, I think I might be able to tolerate that more readily than I can this way. But that's going to make it awkward to use. And I want the machine easy to use. I want my cake and I want to eat it. How rude. Okay. This is a little bit more complicated than I was hoping it was going to be. And I wonder whether I can help myself by collapsing the design a little bit. If I can collapse the design a little bit. For example, if I moved the ball screw and put it up here, that would shrink this down. Yeah. Yeah. Yep. If it was easy, everybody would do it, right? Okay, more problems to solve. I think rather than torture you guys in me like trying to figure this out, I'm going to take this offline. And I'm going to have a little play around with it and see whether or not I can make something work. And then get the order placed, because it's going to take a couple of weeks for the components to turn up from AliExpress. Let's have a look at the order time. 11th of November to the 18th of November. It's going to take for these parts to turn up. So that being said, I mean, they've got plenty of quantity of the 700s. They've got plenty of quantity for the 600s. They got plenty of quantity for the 1100s. So that's absolutely fine. That's fine by me. So let's do that. Let's take this offline and I'll figure this out. And then once I've placed the order, I'll consolidate the learnings of everything that I've done in these live streams to this point. And I'll upload a video summarizing the design to this point. I think that's probably the best thing I could do. Right then, guys, thank you so much for hanging out. Have fun, be safe. I will catch you in the next video, and yeah, there will be some progress made in the days to come, because I've got time on my hands. So until next time, see you soon.